Hi and welcome to another chemistry lesson, and we are still looking at chemical energy changes, specifically the Maxwell Boltzman energy diagrams. And in the previous video we explained what this diagram is, and in this video I'm going to look at how factors changing the reaction rate actually affect these diagrams. Okay, so here again is an example, or my best attempt at a Maxwell Boltzman energy diagram. So we have probability on the vertical axis, and that tells me what is the probability of observing a certain level of kinetic energy. So you can see the probability of observing kinetic energy here is the highest, and we called that the modal kinetic energy. Okay, that's the highest kinetic energy, and then on average would be slightly higher, in this case slightly higher than the modal kinetic energy. And the reason for that is because of some outliers. Okay, so the average is probably somewhere there, and the reason for that average kinetic energy is because we have some outliers. We have some particles with so much kinetic energy that on average it pulls the whole average up a little bit. Now we said in order for the reaction to occur we need to have successful collisions, and the energy level at which we have those successful collisions is called the activation energy, and that occurs right about here. Okay, so this is the activation energy, and only particles that are falling in this energy level will have sufficient kinetic energy in order to cause successful collisions. Okay, so this was the standard Maxwell Boltzman energy diagram. Now our question is, what would happen if we add heat or light to this system? So if I were to add heat or light, okay, what I mean is I'm adding energy to the system. What I'm literally doing is I am increasing all of the energy levels. So when I add heat or light, I'm literally adding energy to every single particle in that existent in that reaction. Now what that would do is that this particle that used to fall here will now increase his energies, his kinetic energy. So he will move to the right, and that would literally cause the following to happen. Okay, this whole thing moves to the right, including the modal and the average kinetic energy, because the modal and average kinetic energy refers to the actual molecules, but the activation energy doesn't increase. Okay, it doesn't also shift. Activation energy is literally just the amount of energy that I need for the reaction to occur. Average and modal kinetic energy is the average and modal kinetic energy of the actual particles. So now what I want you to notice is that notice how the area under the graph represented the probability of particles actually having successful collisions. Okay, now look where that area under the graph is. Okay, now this is the area under the graph. Okay, here we go. That's the area under the graph now. Okay, and you can see it's now much more. So the probability of having successful collisions are much more, and it makes very common sense if you understand that all the particles have their kinetic energy increased. So the likelihood that some particles now fall above the activation energy is exactly must have increased as well. Okay, so that is one way in which we can increase the reaction rate, is increasing the probability of having successful collisions by adding heat or light to a system. The next one we looked at was to add a catalyst. So again, if this is our standard reaction occurring at standard conditions, nothing added, room temperature, etc., and we were to add a catalyst, okay, add a catalyst. What does a catalyst do again? Well, you might recall from our energy diagram, our probability, our internal energy diagram. Okay, when we had internal energies on the vertical axis and time on our horizontal axis, we had the diagram look like this. Okay, this was when I had more internal energies before and less later, which means I will release energy, the excess energy, in the form of heat. So this is exothermic, an example of exothermic, and this was the activated complex. And if we added a catalyst, it reduces the activated complex, in other words, the amount of energy that I need in order to have successful collisions. So it looked like that. Okay, it looked like that. I think so. Let me actually do it slightly different. It looked like this. Okay, it reduced the activated complex. Okay, it might significantly reduce it. Okay, let's actually significantly reduce it. Okay, like that. Okay, and now you might also recall, hopefully you do, that this level of energy was the activation energy. Okay, the activation energy is the difference between the internal energy and the activated complex. Now notice that the activated energy is much less. So what will happen if we reduce the activation energy? In other words, I need less than that. Okay, now that is my activation energy. So now look at the area under the graph that's higher than that. That represents all the particles that have enough energy to have successful collisions. Okay, and we can see again a much greater area under the graph is being represented here, which means there's a higher probability of having successful collisions. So a quick recap, heat will move this whole graph to the right, okay, causing the activation energy to be relative to the previous graph. It would be less. A catalyst, however, actually changes the activation energy to move to the left, causing a bigger part of the graph to be on the to the right. Now the third thing that we looked at was well, let's quickly go through. The first thing we could have looked at was to increase the actual energy level of every particle. The next thing we looked at is to change the activation energy by adding a catalyst. The third thing we looked at was depended on the type of element that or the phase of the element that I was working with. So if I was working with a solid, it was recommended to increase surface area, okay, by grinding it into a powder or at least cutting it into smaller pieces. If I was working with a gas, we recommended that you increase pressure, okay, or decrease volume, and increasing pressure is the same thing. Okay, increase pressure. And in a liquid, or in or rather more accurately, if I'm working with a solution, okay, that means that my my reactant is being diluted in a solution. Okay, it would be to increase the, let me be constant, increase the concentration, and that meant for every particle of liquid versus a reactant, I should increase that ratio, so that there's just a higher likelihood of actually having reactant particles. Now when I do this, so far we've looked at actually moving this diagram by increasing kinetic energy, changing the activation energy. But when I do any of this, I am literally affecting the probability. Okay, if a solid is increased in surface area, there are more probable or there are more molecules that have a probability of having successful collisions. It didn't change the kinetic energy, it just has a higher probability of having a successful collision. Now what that does is it actually changes the shape of this graph and moves the modal kinetic energy, okay, to the right. Okay, so this modal kinetic energy that we have at that point is moved to the right. It doesn't necessarily change the average kinetic energy. Okay, all of them still have more or less the same kinetic energy, but the point is more of them are now likely to reach that activation energy. So I'm going to attempt to draw it. So my modal kinetic energy might now be somewhere there. Okay, and so it slightly looks like this now. Okay, and that is definitely my best attempt at that. It's not a very nice or smooth curve, but again, notice how we now have an additional percentage of my graph falls. So it's both this purple I had colored in original and this additional green percentage that is also now higher than the activation energy, which now means that I have an increased probability of having successful collisions. Now those are the three changes I could make. I could either change the total kinetic energy of everything, the activation energy to lower that, or the probability of actually having successful collisions by increasing the possible likelihood of those collisions in solids by increasing surface area, gas increasing pressure, and in liquids or in the solution to increase the concentration when it's in a solution. Well, thank you very much for watching. I hope this was insightful and that you actually see that though it is quite technical and slightly difficult, it's really not that strange, and you can figure it out just by thinking of it. Thank you very much for watching. We'll see you in the next video.